Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on March 3, 2026, just yesterday. It uncovers a fundamental scaling asymmetry where vision requires significantly more data than language, and demonstrates that a high granularity mixture of experts architecture effectively bridges this gap. The paper is titled Beyond Language Modeling, an Exploration of Multimodal Pre-Training, and as we'll see later, the findings on emergent world modeling are really impressive. Alright, Figure 1 lays out the roadmap for this study. The top panel illustrates the unified architecture, where a single autoregressive model handles both modalities simultaneously. It performs standard next token prediction for text, but uses next visual state prediction for images, treating them as a continuous sequence. Below that, the figure highlights the 5 experimental axes. The authors systematically explore visual representations, data mixtures, world modeling capabilities, architectural choices, and scaling behavior to understand how these factors interact. Well, zooming into the architecture design, Figure 3 compares 2 ways of handling the model's processing layers. The dashed line represents a standard approach with a shared feed-forward network, or FFN, for both vision and text. The solid blue line shows the proposed modality-specific approach, where text and vision get their own dedicated parameters. Because the chart is plotted so that better results are always further out, the solid line encompassing the dashed one indicates that separating the modalities improves performance on every single axis. So, having established the architecture, Figure 2 introduces the diverse diet of data used for pre-training. The inputs fall into 4 distinct categories. At the top, we have standard text, followed by image-text pairs that align visual features with language. The third row is critical for world modeling. It uses action-condition sequences, where the model predicts the next view based on a movement command. Finally, raw video clips at the bottom teach the system about temporal dynamics and physics. Okay, while Figure 2 introduced the data categories, Table 1 investigates the distributional gap between standard text and image captions. The authors measure this using cosine distance, where a higher score indicates a larger difference in style from the pre-training text. Standard metaclip captions are relatively close at 0.2. However, the recaptioned data in the center column jumps to nearly 0.3. This larger gap explains why training on synthetic captions can degrade performance on pure text tasks. So, Figure 21 summarizes the final architectural decisions by stacking improvements one by one. It tracks 2 metrics: text perplexity in orange, where lower is better, and the DPG score for image generation in blue. First, separating the feed-forward networks for each modality gives a solid initial gain. Then, selecting SIG LIP2 as the vision encoder significantly lifts the generation score. But the real game changer is the mixture of experts architecture in the third section, which slashes perplexity and boosts generation simultaneously. To wrap it up, switching to X prediction provides the final nudge to reach optimal performance. Alright, since Figure 21 identified the mixture of experts as a key driver, Figure 25 now quantifies exactly how it scales. The charts display language analysis in the top row and vision in the bottom. The third column is particularly revealing. It plots the optimal training tokens against compute. We see language scaling with an exponent of 0.59, while vision is steeper at 0.64, confirming it is more data hungry. Yet the comparison panels on the far right show that the mixture of experts design narrows this gap significantly compared to dense models, which helps harmonize the training. So wrapping up, 2 big takeaways stand out. Vision is fundamentally more data hungry than language, and the mixture of experts architecture is the key to balancing this asymmetry efficiently. Broadly, this research implies that future foundation models will evolve beyond simple language tasks into unified systems capable of modeling physical reality from scratch. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.